Welcome to an overview and demonstration of Apache Spark and Apache Kafka. Spark is a popular distributed compute framework optimized for large-scale parallel data processing. It was originally developed by a group from UC Berkeley to address some of the frustrations of using MapReduce. It is currently an open source project managed by the Apache Foundation. Its core objective is parallel distributed computing that is fast, efficient, and fault tolerant. It should be noted that Spark is awesome. It integrates with almost every database, object store, streaming framework, and input source out there, and it also supports many programming languages. A typical Spark setup consists of three components: a driver program that an ETL engineer would write to submit a job to Spark, Spark's cluster manager, which allocates subtasks to one or more workers, and the workers who do the job. Spark's use cases include ETL and SQL batch jobs, stream processing, analytics, and machine learning tasks. The Spark ecosystem consists of a distributed SQL query engine, a streaming framework, a machine learning library, a graph processing framework, and various language APIs. Kafka is a distributed messaging and streaming platform optimized for real-time processing of high-bandwidth streaming data. Originally developed by LinkedIn, it is now an open source project. There are four major components of the client API that allow clients to produce or consume data streams, to split or combine streams, and to integrate streams with existing databases or data stores. A Kafka cluster consists of one or more brokers that distribute, load balance, and persist streaming data. Zookeeper is used for inter-broker coordination and leader election. Producers push data to the brokers. Consumers receive data from the brokers. A topic can have one or more partitions, allowing each member of a consumer group to process a subset of the data stream. This is great for parallel processing. Typical Kafka use cases are high bandwidth messaging, web activity tracking, distributed metrics aggregation, centralized log aggregation, high bandwidth, high throughput stream processing and data pipelines, event sourcing or change tracking, and commit logging and cross-node resyncing. So why should we use Spark with Kafka? Well, Spark and Kafka work extremely well together. Kafka can partition data and serve subsets of it to multiple members of a single consumer group. Also, Kafka provides fault tolerance by requiring consumers to increment their offsets with the broker after each transaction is completed. Spark is designed to distribute subsets of data to multiple workers to provide parallel computing. Combining Kafka and Spark can provide a fast, reliable, and scalable streaming pipeline. Let's take a look at Spark and Kafka in action. There are four approaches for deployment. The simplest method is to deploy containerized services using Docker Compose. This is the approach used in this demo. It's great for rapid deployment of a sandbox cluster, but it lacks production-grade features such as auto-scaling, load balancing, and storage provisioning. The next method is to deploy containers using an orchestrator, such as Kubernetes. This is the recommended approach when deploying for production. This approach supports auto-scaling, which is scaling up additional workers as needed and scaling down. Load balancing, which ensures jobs are distributed evenly across compute nodes. And storage provisioning, where a storage orchestrator can provision persistent storage that can be shared by workers across nodes. The next method is to deploy on a Hadoop cluster. This is the recommended approach when interoperability with Hadoop is a requirement, such as integration with HDFS, Hive, HBase, or Cumulo. In this configuration, Spark can still use its standalone job scheduler or offload scheduling to Yarn, which is Hadoop's scheduler. The last method is to install the needed executables and libraries on each compute node. Please do not use this approach. For this demo, Docker Compose was used to deploy the needed services. Compose is a YAML-based tool for defining and running multi-container applications. Bitnami is a great source for ready-to-go images and Compose files for tons of popular cloud and big data tools. The Compose file for this demo uses several snippets from existing Bitnami Compose files. Here's a GraphViz diagram of the Compose file used to deploy a mini data platform for this demo. It consists of one Spark manager and two Spark workers, Jupyter Lab with a persistent volume and a shared volume with the Spark workers to allow input files to be shared between Spark and Jupyter notebooks. Apache Kafka HQ, a popular web UI for managing and monitoring a Kafka cluster. A single Kafka broker with a persistent volume. Zookeeper with a persistent volume. A Python-based data simulator that simulates grocery store transactions and sends over a Kafka topic. MariaDB, a MySQL-like database that serves as the grocery store database with a persistent volume. PHP MyAdmin, a popular web UI for interacting with MySQL-compliant databases. Cassandra with a persistent volume. This is a big table compliant data store that will serve as an example data warehouse. And finally, SQLPad, a web UI for interacting with SQL and SQL-like databases, including Cassandra. Also, the Compose file is configured to expose all the ports needed to access the various web interfaces from a web browser. The mini data platform is started by running Docker Compose up. Docker then downloads all the needed containers, creates a virtual network, creates all the necessary persistent volumes, and then starts up all the services in the correct order. Docker will monitor the health of each service and will restart any crashed containers. In this first ETL example, a delimited text file containing a product catalog is imported into a Spark data frame, and a few transformations are performed on it. Next, a table containing grocery store transactions is imported from MariaDB into another data frame. Then the two data frames are joined and written to Cassandra. Then a new static data frame is created containing metadata and is joined with the combined product and transaction data frame and is written to a Kafka topic where hypothetical downstream consumers can consume and process. The first input is a file containing the grocery store product catalog. The second input is a grocery store transactions table from MariaDB, as shown here in SQLPad. This ETL example is written in Python using the PySpark API. Here is the Jupyter Notebook. The first cell contains all the necessary imports for this demo. Next, a Spark session is created, specifying a name for the session, the URL to the Spark master process, and a list of dependencies that are needed for this job. The list of dependencies includes connectors for MySQL and Cassandra, the Spark SQL library, and the Kafka library. Spark workers will download these dependencies from Maven Central. When executed, a session is created and the Spark workers retrieve the required dependencies. The Spark Web UI shows that a new session has been created and is assigned both workers. Here, the product catalog file is loaded into a data frame and the first 20 rows are printed. It's important to note that this file was read in by the external Spark workers and the data frame exists in their memory space. No processing was done in this Jupyter Notebook. A few transformations are performed on the catalog data frame before printing the first 20 rows again. First, all missing item types are filled in with the string other. Next, all string fields are capitalized. Finally, all column names are converted to snake case. Once again, these instructions are executed in the Spark workers, not in this notebook. Also, the instructions are deferred until it's necessary for them to be performed, which in this case happens when show is called on the data frame. Next, grocery store transactions are loaded from MariaDB into a data frame and the first 20 rows are printed. The MySQL connector is used even though the database is MariaDB. There were some compatibility issues using the MariaDB connector, so the MySQL connector was a better option. An inner join is performed on the two data frames using the SKU field. Then the first 20 rows of the new data frame are printed. Here is the schema for the new data frame. Cassandra needs to be set up to receive the combined data frame. A connection is established using the Python API and a new key space is created. A Cassandra key space is roughly equivalent to a database in MariaDB. Then a new table is created in Cassandra that matches the schema for the combined data frame. It would be nice if Spark or Cassandra provided a way of auto-creating the table from the data frame schema, but no such luck. Now the data frame is written to Cassandra by Spark using the Cassandra connector. Next, a static data frame is created for metadata related to the transactions just performed. The metadata contains source information pointing back to the product catalog file and the transactions table in MariaDB, and destination information pointing to the newly written Cassandra table. Here's the schema for the metadata data frame. The metadata is joined with the combined product and transactions data frame and is written out to the Kafka topic persisted. Since Kafka records are key value pairs, the ID from the transaction table is used as the key and the remaining fields for the value. Lastly, the Spark session is closed. It is important to close a Spark session or terminate the driver application to free up the allocated Spark workers. The Spark Web UI provides some useful views containing task information, metrics, and logs. These views can be useful for debugging and monitoring. Here's a view of worker and driver metrics. In SQLpad, it can be verified that the combined data frame was successfully written to Cassandra. Kafka HQ shows that 1.5 million records have been written to the Kafka topic persisted. Here are the contents of an individual Kafka record. The key is the field ID from the MariaDB transaction table. The body is a combination of product data, transaction data, and metadata. In this next ETL example, the product catalog text file is again imported into a Spark data frame, and some transformations are performed on it. Then a Kafka consumer is created to consume a continuous stream of transactions from the data simulator. The product catalog data frame is joined with each streaming data record and then is written out to a different Kafka topic based on the name of the manufacturer. In this scenario, each manufacturer has a hypothetical downstream consumer to funnel this data into their respective data stores. This is an example Kafka transaction record from the data simulator. Back to Jupyter, the first cell contains all the necessary imports for this example. Next, a Spark session is set up like the previous example. The only dependencies are the Spark SQL and Kafka libraries. Also, a location to store input stream checkpoint data is needed to handle fault recovery. Next, the product catalog file is loaded into a data frame and several transformations are performed on it. Once again, all missing item types are filled in with the string other, all string fields are capitalized, and all column names are converted to snake case. Since the manufacturer's name will be used as a Kafka topic, Prefix the name with vendor underscore and replace any characters that are not valid in Kafka topic names. Then the first 20 rows are printed. Here, a new structure is created that matches the schema of the Kafka stream that Spark will be consuming. This struct will be used by Spark to marshal the JSON formatted messages into a structured data frame. It would be nice to skip this step, but Spark does not currently provide a method of inferring the schema of incoming JSON data. Here, a streaming data frame is set up to listen to the Kafka topic named transactions. Setting the format to Kafka tells Spark to use the Kafka API. Spark is told to convert the raw incoming bytes into a string and then to marshal the string into the structure format from the previous step. Since this is a streaming data frame, it contains no data until start is called on it. An inner join is performed between the static catalog data frame and the streaming data frame using the SKU field. This new data frame will be written out to Kafka. The message topic is set to the manufacturer column. The key is set to the SKU column. The value field is restructured to contain separate sub-objects for transaction, product, and inventory information. Then at the bottom, the schema for the new data frame is printed. Since the join includes an unstarted streaming data frame, the join is deferred until after the streaming data frame is started. Here, the streaming data frame is started, and the contents of the join data frame start getting published over Kafka. A join operation occurs for every incoming message in the data stream. Since this is a streaming job, it will never end unless the subscription topic is deleted or the driver application is killed, so this stop call will never happen. It is recommended to have dedicated Spark workers for long-running streaming jobs to avoid starving short-duration batch jobs from access to workers. Kafka HQ shows that Spark has an active consumer on the transactions topic. The Spark UI shows that each message is treated as a separate subtask. Here is a table of previously processed messages. The Spark UI also provides some useful streaming statistics and metrics. It also generates a diagram of the DAG being performed on each incoming message. Kafka HQ shows that a topic is being created for each manufacturer. Here are the contents of an individual Kafka record sent to a manufacturer. The key is the SKU field, and the value field consists of the three sub-objects. Now for some parting thoughts. Spark's pros include: it's a very fast distributed compute engine. It attempts to keep as much data in memory as possible to reduce computation latency. It supports lazy evaluation, allowing a developer to chain together many operations and to defer actual computation until necessary. Spark has support for multiple languages, including Java, Python, Go, R, and all .NET languages. It provides a great set of fault tolerance and recovery features. Spark can be integrated with almost any database, data store, streaming framework, and so on. Spark is better than MapReduce. It is easier to learn, provides more built-in operations, plus a library of machine learning algorithms, and benchmarks show it to be faster. Spark's cons include a fairly steep learning curve and can take a long time to master, though I found that its recent transition from resilient distributed datasets to Panda-like data frames makes it more beginner-friendly. Sometimes manual optimization is needed, such as tweaking the number of workers, cores, data partitions, heap size, etc. to get optimal performance. Spark ships with fewer machine learning algorithms than, for example, sklearn, but a third-party library called Sparkling Water adds a lot more. Spark's data partitioning can result in many small files, which can really bog down a distributed file store. though this is really only an issue with Hadoop's HDFS and AWS S3 compliant object stores. Spark's stream processing is technically not real time because on a periodic basis, Spark ingests a micro batch of stream records, though in practice this seems to be a non-issue. The web UI needs a lot of work. It's difficult to host behind a load balancer and is lacking in useful visualizations. And out of the box, Spark has poor back pressure handling, though in production, auto-scaling and low-latency distributed storage can mitigate this. Some important things to remember if you decide to try out Spark for yourself. Use Spark in a container. It's much easier to deploy and configure. Remember to always stop your Spark session at the end of a batch job or allow the submitting application to terminate. Differences in Python and Java versions between the submitting application and the Spark workers is the leading cause of errors during job execution. Computations do not immediately execute. They are deferred until necessary, such as printing a data frame or writing it out to a database, file system, or a streaming service. For streaming jobs, you should use dedicated workers for long-running streaming jobs, or batch jobs will have a tough time getting execution time. Adding multiple workers to a streaming job does not guarantee parallel processing. The streaming topic needs to be correctly partitioned, or you will end up with idle workers that could be taking resources away from other jobs. You should explicitly define the number of Spark workers to allocate to a streaming job, and it should never exceed the number of partitions defined for the topic being consumed. In summary, Spark is a powerful distributed parallel compute engine that is scalable and fault tolerant. It is useful for ETL and SQL batch jobs, stream processing, and AI/ML applications. Kafka is a real-time streaming framework that is also scalable and fault-tolerant and is a great backbone for data pipelines. Spark and Kafka work seamlessly together. Where can you find more information? For Spark, Databricks is currently the thought leader in the Spark community. Also, the awesome Spark repo on GitHub is a great source for finding books, documentation, tutorials, add-ons, and other resources related to Spark. For Kafka, Confluent is the thought leader in this area. Also, the awesome Kafka repo on GitHub is a great source for all things Kafka.